There we go. Okay, so I'm gonna do it. Well, I can't do it this way because the screen recorder or the streaming mechanism can only stream from one of the screens, and I don't know which one it's locked onto. So I don't want to do the split setup where you can look at the homework assignment on one side and look at Logisim on the other side, because otherwise that might mess up the recording. So what I would do is I'm just going to kind of switch between the screens, so this way it doesn't interfere with the recording or the streaming. Okay, store, and I'm going to do the homework assignment for the addition. Now there are many ways to do it. Okay, so by no means am I implying that what I'm going to do is quote unquote the right way to do it. It's one of the many ways to do it. Okay. And just to discourage people from just copying this solution, I'll make this the painful solution. It's Logisim generic. There we go. All right. So I'm going to turn this into the really painful way of doing it by not using any multi-bit gates. Because by using multi-bit logic gates, it's like clean, ding, 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 you're done. Wow. The only thing that's sort of complicated would be the individual case, okay? But if you don't, it gets kind of hairy. So, but I will still make it organized to the point where you can understand what is going on. Okay? So we'll pull some input pins first. Okay, so we have 3 input pins, of which 2 are 3-bit wide and 1 is only 1-bit wide. So this one is X, this one is Y, and this is carry in, which is represented by C in. These 2 are 3-bit wide. So 3, 3. So, and I did say that I don't want to use the easy way to do it. So I'm going to have to leave myself a little bit of space here because I need a lot of splitters to do it. Well, actually, I don't need a whole lot of splitters, but I need a lot of space to put all my components. So I'm going to put a splitter here. Now, when you use splitters, you can control where it splits. So you can control that by the appearance. So this is going to be 3-bit, and I need all 3 bits split. So we'll put it here. That is that. And it's going to be the same setup for the other one, so I just duplicate it for Y. And here's a C in by itself. Okay, so this is how I split the inputs from one single input pin that is multi-bit into the individual bits. Bit 0, bit 1, and bit 2. We have to generate the P's and the G's, right? The P's are the disjunctions and the G's are the conjunctions. So we go for those gates. So we shrink these to 2 input gates and make it as small as possible because we have a whole bunch of these. Okay, so we have 1, 2, 3. So these are the G's, and then we have a bunch of OR gates. Same thing, 2 bits. Make it a narrow, like so. 1, 2, 3. Okay. So we just have to make some connections here. This one goes here, and this one goes here. Here, this one goes here, this one goes here, and that one goes here. And then we have to do the same thing with all the OR gates. So we have to tap this line to go here, tap this line to go here, and then we go to the second one. Oops. Nope, that's wrong. undo this one. There we go. So this one goes to the second one. Now the order doesn't seem to be important, but if you want to do the next homework assignment, they become important. So this is also where I don't want to make it easy for you guys, so I'm gonna make the wrong connection here. If there's a way to do this wrong, I'm gonna do it that way. Well, it will give me the correct result as an adder, but if you apply it to the subtractor, it will give you the wrong result. Okay, so with the third one, let's see, that goes here, and that goes here. Okay, that should be confusing enough. Okay, so now I have all the X signal, all the Y signal, I have all the G's, which are the conjunctions, and all the P's, which are all the disjunctions. Okay. Now, there's one thing that you can do if you do it this way, like you have all the individual bits flying everywhere. You can use the concept of tunnels. It is exceptionally useful for documenting your design, and also it can make your design so that you can put one portion over here, put one portion over here, put one portion over here, and it will still be easy to understand in the end. Okay, so I'm going to show you guys how to use tunnels. So tunnels are under wiring, and these are tunnels. So each tunnel doesn't look like much. I mean, each tunnel is nothing more than just a little symbol. And if you, I may not have enough space to do it. Okay. I'm just trying to figure out where to put all these tunnels, because I don't have enough space. Okay, let's zoom out, zoom out.
Can you make this tunnel smaller in size?
No. It didn't grab the carry pin. There we go. Grab everything, move it down. There we go. Okay. So I'm going to have some tunnels here. 1, 2, 3. And tunnels can be labeled. Now, the labeling of a tunnel is not really just for documentation purposes. It is also the name of that particular wire. In other words, if you have two tunnels and they are referring to exactly the same name, they are the same node. They represent the same electrical node. Okay? Which is really helpful, because now you can actually put a design somewhere here, put some of the design over there, and they are logically connected. Okay, so I'm going to show you guys how to do that. So by making this design, as convoluted as I possibly can, I'm also illustrating some of the features that will help you, get this design to work, even though it is convoluted. That's 2. And that's 3. And I'm going to make the Y's over here. So we'll have more tunnels. And this time we'll make it face the other direction. Oops, no, that's not what I want. Okay. 1, 2, 3. So that would be Y0. Y1 and Y2. There we go. So Y0 goes to bit 0, Y1 goes to bit 1, and Y2 goes to bit 2. There we go. And I can have one for carry in. So with this one, I will make a tunnel that faces north. Okay, and you can certainly do it that way. And this one I'm going to label as K0. Because C in is K0. So that means, I'm starting to use the same terminology as in the expressions in the notes. Yep.
Are we recording this?
I...
Yeah, you can see it live on this channel.
Oh yeah, you can see it. Yep, it is recording. No, it's streaming, not recording.
Okay.
Yep. There was one time I was teaching a class, and about 10 minutes into the lecture, someone in the class got a call from a student who was en route to the class, saying that I forgot to turn on the audio. Because somebody was watching, the streaming in a vehicle, when somebody else is driving, and noticed that I did not turn on the audio. The mic was not set up correctly, and then called one of the students in class to let me know that I forgot to switch the audio channel.
I think you just hoped someone else was driving.
Huh?
I said, I think you just hoped someone else was driving.
Yes.
That was Shane last semester, right?
Ah, yeah, it was.
Yeah.
Was he driving himself?
I kind of think he might have been. I don't know.
Oh my goodness, that would not be very healthy.
This is,
And then we have 6 of these for all the P's and all the G's. There we go. So yes, the use of multi-gate, multi-bit gates will definitely make this design a lot easier. But I don't want to give away that one until the subtraction homework assignment is due. Okay, so this would be G0, G1, G2, P0, P1, and P2. There we go. So now we got every individual bit available. So it's time to look up the equations. Okay, so we'll go back to the notes and look up the equations. The modules, look at the binary addition. And they're all basically spelled out already. So when you look up K1, the equation of K1 is already spelled out all the way up to K3, which is basically all that you need for this homework assignment. There we go. So we got K1 is G0 or P0, K0. Okay, so I'm going to just go down here and then start to make my subcircuit down here. So that would involve a AND gate and an OR gate. So we have an AND gate. I'm just making copies of this because I can, and the OR gate. So can someone remember which two? Okay, so the AND gate is ANDing the P0 and the K0. So this is where the tunnels can be very handy, because then I can just put some tunnels over here, change the direction so that each one is just coming from a particular tunnel. And of course the output goes to another tunnel, a tunnel on its own. There we go. Alright, so going back to here, I just look at the equation. G0 is on its own. So this is G0, which is on its own. And then we have P0 and K0. You can also see the moment I give the tunnel a name, the wire changes color. Because it changes color from blue, which is basically saying, I don't know what it is, to either dark green, which is a 0, or light green, which is a 1. But since everything is a 0 at this point, they're all going to be dark green. Okay, so there are reasons why the wiring changes color as soon as I give them names. This is the output, and this output is K1. So we just put K1 over here, done with one of the carries. Are we doing okay so far with this method? Okay, not particularly efficient, but it's easy to do because we spell out every single thing, and there are no real tricks involved other than the use of the tunnels. Okay. So this next one is K2. So K2 is a little bit more complicated. It needs a bigger OR gate and then 3 AND gates here. So we'll go ahead and just copy and paste it and do some extensions, do some changes to this thing. Okay, so we'll disconnect certain portions, turn this into a 3-input OR gate. And the red line is basically saying that we have two things outputting to the same wire, but they are conflicting. Okay, so we want to change this one to a K2. And then we look at K2. It has got G1 on its own. So we'll put this one as G1, which is on its own. Whoops. Said one thing, did something else. Okay. The other one is P1G0. P1G0. We can change this one. P1 and a G0. And then we are just missing the one that has 3 inputs, the AND that has 3 inputs. Okay, so we pick an AND gate, duplicate it, and say that this one has 3 inputs. And we can also see if we already have those particular tunnels already done, because if so, we can just duplicate. So we got the K0 that we can duplicate from here. And we need a P0 that we can duplicate from here. And we need a P1 that is, oops, did I make a mistake? Nope, P1 is also here, but we can tap the same wire twice. So we have K0 goes here, P0 goes here, and then P1 is the same, so we can just tap it like that. And then the output of this AND gate goes into one of the inputs of the OR gate. Now we have K2 done. Any questions about K2? Okay, now we can work with K3. So when we work on K3, I'm just going to be lazy and just copy and paste this down here. LogicSim automatically extends a page, when you have more components. So when we look at K3, which is the most complicated one that we have, has got these components. So we'll go ahead and start to make some changes. Turn the gate into a 4-input gate, and it looks better if we just use a medium size. Oh, okay, it's not. It messes up the connections. Okay. So this is the 1 input, 2 input, 3 input, and then we have a 4-input AND gate that I'll put here. All right, so we look at the equation. The 1 input is a G2, so change this to a G2. This is output K3. Okay, so quick question. What is the difference between a tunnel versus a pin? They both can be labeled, right? You can make wires to connect to either one, but the purposes of these two are completely different. What is the purpose of pins?
It's just the start, pretty much.
The start and the end. Go ahead.
I was going to say, yeah, it's like an input that you can change from 0 to 1.
Right, they are the interface to the entire circuit. Okay, they're like parameters in a function. What about these tunnels?
They just take you from one place to another.
Yep. They're basically shorthands, right? Take this, and we will reuse it over here. In other words, if you look at pins as parameters, you can look at input pins as pass by value parameters, because they're only serving the purpose of getting something into a circuit. The output pins are kind of like pass by reference parameters, because you can use it to reflect the result of a calculation. Then the tunnels are more like local variables, because you're just assigning names to some partially computed things, but they can only be used inside this overall circuit. They do not appear when you take this circuit and turn it into its own component. They do not appear anywhere. The tunnels are only used internally. So they're more like local variables within a function. Okay. All right, so we got G2 done, and then we have P2G1. So we have P2 and G1. And then for the 3-input one, we got P2, P1, G0. So we got, okay, turn this into G0. And between the 2 and the 3, they share a P2. So P2 is already shared. And then we have a P1. So we can turn this into P1. And then the 4 input one needs K0, P0, P1, P2. So we'll take a K0 from here, or if you prefer, you can pull a K0 just like that. It's just messy, okay? Yeah, but it's equivalent of making another tunnel over here with K0. So we got K0. We need P0, which we have here. Well, we'll go ahead and make a tunnel. So we pull another tunnel of P0 and stash it here. P1 and P2 are both found here. This is P1, this is P2. So I'm going to do P2 over here, and then we have P1 over here, and then this. Okay, I'm making this look a little nicer because I could have crossed over the wires, but oh no, not yet. There we go. And we have K3. Okay, so once we have all the Ks, what do? We have to do the result, okay? So the first thing we have to do the result with, according to the equation, is between the X and the Y. Once we have the result of X and the Y, then we take that and then we have another result with the Ks. Then we have all the sum bits, okay? That we can do relatively quickly, okay? So I'm gonna do that circuit over here. And I also add in your homework assignment that you can use the exclusive OR gate explicitly, which saves a little bit of design. So we take the exclusive OR gate, which looks like this, turn it into a narrow one with only 2 inputs. And 1 input comes from X, 1 input comes from Y. So we'll go ahead and just copy the XY here. I could have just changed. I'll just copy and paste here. So 1, 2, change this one to X0, and this one to Y0. This output, technically speaking, is your Q0, but I don't really need to represent it because it is used immediately by the next exclusive OR gate. So that's why it is not represented. It doesn't have a name on its own because it doesn't need it. There we go. And what goes into here will be which one? K0. Very good. So we'll take a K0, or we can just always just kind of do it like this. K0. And what comes out of this? S0. But I don't want S0 to have its own pin. Remember, I want the sum to be a 3-bit output pin. Okay, so I'm gonna let it dangle for a while because what about S1, bit 1 of the sum? What is it gonna look like? It looks exactly like that. We change all the zeros to ones, right? And then S2 is gonna look like this. We change all the ones to twos. So we're gonna copy, paste, and modify. Now, just like what I have talked about in class a few times, every time you copy, paste, and modify, you really should ask yourself, is there a better way to do it? And obviously, in this case, the better way to do this is to use multi-bit gates. But I just did not want to give you the clean and easy solution before the subtraction or subtractive homework assignment is due. Then I'll give you the clean and easy solution so that you guys will go like, well, some of you will go like, oh, why didn't you give me that to begin with? But I want you to kind of think about it, okay? Because this is your homework assignment. I want you to think about how to make the design look cleaner and also save yourself a lot of time in the process. Okay. 2, and 2. Okay, so now that we have S0, S1, and S2, we can use a splitter to turn it upside down or left side right and make it into a merger. Okay, so we can merge those back into the sum output pin. So we take one of the splitters that we already have up here, duplicate it, and move it to where we need it. There we go. Make it face the other way, face west. So you can see the bits are already in the right order, because the worst thing that can happen to your design is you got everything right, but when you merge the bits, you got the opposite order. That would not be very pleasant, because then your result would actually be wrong, even though you got the design correct. Okay, so we want this to be a 3-bit output pin labeled as for sum. And then we also have one extra output bit, which is K3. So you can either turn the K3 into an output pin, or you can just attach an output pin to this one. Either way is fine. So we label this as C out, carry out, and the whole thing is done. So now it's time to test it. Now to test this one, because it is all over the place, it's a little bit hard to see, right? So one thing I can do is to move these guys up. Okay, first of all, we have to disconnect these guys here first, because otherwise they will just cross over everywhere, which is not easy to read. So we put this one all the way up here. At least we can see it along with X and Y. And get this one up to about here. And of course, we can always apply K3 as a tunnel here, and we can also give this one a label. So we put another tunnel over here. And guess what? A tunnel can also be multi-bit. So we call this one S, and then we just attach these guys over here. 2 more tunnels. Turn this one to sum and make it 3-bit wide. And the other one is K0. Oh, it's K3. There we go. All right. So this way, it is just easier for me to look at the input and look at the output and see whether they make sense or not. Well, guess what? This is one test case already. We are looking at 0, 0, 0 plus 0, 0, 0 with carry in as a 0. The output, the sum, is 0, 0, 0, and there's no carry out, or the carry out is a 0, 2. That works. Okay, so we can play with it a little bit and just turn this into a 1. The sum is a 1. That's good. So that is good so far. Let's see what is 1, 0, 0 plus 1, 0, 0. It is 0, 0, 0 with a carry of 1, which is good. Okay. What about 1, 1, 1 plus 0, 0, 1? It is also 1 followed by all zeros. That's good too. So far as I can test it, it seems to be working. I can turn Y into a 0, turn C in into a 1, and I should get back exactly the same result as last time, and it did. Now, to be very frank, I am surprised that it works, that I did not make a stupid mistake somewhere. With all of these wires flying all over the place, I'm just surprised too that it works. If it doesn't work, I can use that as an excuse to teach you guys how to debug a circuit. If it works, even better. Yep.
Is CN like required to be just like there, even if it's assigned automatically most of the time to be assigned to 0?
No, it's not automatically 0, because in the equations, the whole point is K0 is an input pin. Because when you look at this whole thing, K1 relies on K0 being a variable. K2 also relies on K0 being a variable, and then same with K3. So K0 cannot be assumed 0. Because you can see that in my test cases, like this one, I'm using C in to be a 1 to test my design to see whether it works or not. All right? Are there any questions? Now, how can you tell where you can use a multi-bit gate? Every time you see copy, paste, and modify, you kind of think about, okay, can we use a multi-bit gate over here? Because we are replicating the same pattern. There's one more clue. Okay. The other clue is we are splitting and then we are merging. Okay, if you split, you do some operations, and then the gates all look about the same, and then you merge the whole thing, that's also an indication that you might be able to use a multi-bit gate. And I did not use any sub-circuits. If I wanted to use any sub-circuits here, this would be a good candidate as a sub-circuit, this would be a good candidate as a sub-circuit, and this would be a candidate as a sub-circuit as well. But there are many ways to do it. This is one way to do it. Are there any questions about the look-ahead adder? So now your focus should now be changed to the look-ahead subtractor. So what should be going on in your mind is, okay, now that we know what the adder is, and many of you probably got this right, okay? So the question is, how do I start with an adder and to turn it into a subtractor? Okay, so you want to refer to the notes and look at the differences. The differences between an adder and a subtractor are very, very minor. So you just want to locate those differences, make those changes to your design, and test it, change the labels. Don't forget to change the labels. And it should not take much time to work on the subtractor. Are there any questions regarding the solution of the adder? Okay, no questions. Any questions about the material that we talked about today? Okay, questions about that? All right, if that is the case, I'm going to stop the streaming, and you guys can either stay here and work on your subtractor. You can ask me questions about this particular adder. You can ask me, about your particular design and show me, okay, is this a good design or not? Or you can just go.